My name is Prithvisha Nath and I am the TA for this course, Vibration of Continuous System. I am a PhD student in the Department of Aerospace Engineering at IIT Madras. This is week 5 for this course. So let's start with the first question. Compute the first three natural frequencies of the transverse vibration of a uniform beam of rectangular cross section with this is the cross sectional 100 mm into 100 mm into 300 mm with L 2 meters, E 20.5 into 10 to the power 5 Newton. E equals 20.5 into 10 to the power 10 Newton per meter square, and density is 7.83 into 10 to the power 3 kg per meter cube. For three cases, first is simply supported case, second is when both the ends are built in, and the third is when one end is fixed and the other end is free. So from the question we know the length, the E and the rho, and we can also calculate the cross sectional area of the beam from the given data. So given L equals 2 meter, E equals to 20.5 into 10 to the power 10 Newton per meter square, density is given as 7.83 into 10 to the power 3 kg per meter cube, and area we can calculate 100 into 300 millimeter square, now I'll convert this area into meter square, so that is 0.03 meter square. So I can calculate the moment of inertia I, which is equal to 1 by 12 into 0.1 into 0.3 cube. So this is equal to 2.25 into 10 to the power minus 4. So this is the I for the given cross section. Now we can write omega n as beta n L square root of EI divided by rho A L to the power of 4. Now first I'll calculate the terms in square root. So I will just substitute the values that I have. I have already calculated, and I know the value of E, rho A, and the length of the beam. So I'll just substitute it. So what is the E which I have? E is 20.5 into 10 to the power of 10. I already calculated as 2.25 into 10 to the power minus 4. Density is given as 7.83 into 10 to the power 3, and area is 0.03, and length of the beam is given as 2 meters. So this comes out to be 110.7814. So this comes out to be 110.7814. So we are asked to calculate the first three natural frequencies for each cases. Now for the first case, that is simply supported. For simply supported beam, now we know that for simply supported beam, for simply supported beam, beta 1 L equals to n pi. Beta L, rather beta n L equals to n pi. Now for the first frequency, first fundamental frequency, it will be beta 1 L pi. Now I'll substitute pi in this expression for omega n. That is, omega 1 becomes pi squared into the value which I calculated for the square root term, that is 110.7814 7814. So this is the omega 1. So this comes out to be around 1093.37 radians per second. Now for the second fundamental frequency, beta 2L equals to 2 pi. Therefore, omega 2 can be written as beta 2L whole square into 110.7814. So in place of beta 2L, I'll substitute 2 pi, which becomes 4 pi square into 110.7814. That is equals to 4373.4 radians per second. Similarly, for the third frequency, we'll follow similar step. Now beta 3 L equals to 3 pi. Therefore, omega 3 equals 'So in place of beta 3L, I will substitute 3 pi, which becomes 9 pi square into 110.7814. That is 9840.3 radians per second. So these are the first three natural frequencies for a simply supported beam. Again, we need to find the natural frequency for beam in which both ends are built in. So the second case, that is the fixed beam. For fixed beam. for fixed beam, we know that beta 1L equals 4.730841. So what I need to do, I just need to substitute this beta 1L value in my equation. So omega 1 becomes 4.73 0841 into 110.7814. So into 110.7814, which comes out to be around 2479.3826 radians per second. Now for the second fundamental frequency. For the second natural frequency, beta 2L is given as 7.853205. I'll follow a similar process. So 7.853205, second natural frequency, comes out to be around 6832.2023 radians per second. For the third natural frequency, beta 3L, we know as 10.995608. Therefore, omega 3 is comes out to be around 13393.8474 radians per second. Now the last part of the question, when one end is fixed and the other end is free. So for fixed free beam, here also similarly we have to do the same thing. Here beta 1 L is given as 1.87514104. Therefore, omega 1 is given as so this comes out to be 389.5091 radians per second. Similarly, beta 2L is given as 4.694091. Therefore, omega 2 is 4.694091 whole square into 110.7814. So this is coming to be 2441.011 radians per second. Beta 3L is given as 7.854757 into 110.7814. Therefore, no, beta 3 is given as this. So this is the beta 3L. Therefore, omega 3 is given as 7.854757 whole square 110.7814. So this is coming out to be 6834.9030 radians per second. So this is the first three natural frequencies for the fixed free beam. Now moving on to the next question. Derive the frequency equation for the transverse vibration of a uniform beam resting on springs at both ends. The springs can deflect vertically only and the beam is horizontal in the equilibrium position. So here we are asked to derive the frequency equation for the transverse vibration of an uniform beam which rests on two springs at both ends. So this is my this is the figure. This is the figure which for this question. So we need to find the frequency equation for this beam, for this uniform beam resting on these two springs which are at the end, like both the ends. So I can write Wx equals C1 cos beta x plus C2 sin beta x plus C3 cos hyperbolic beta x plus C4 sin hyperbolic beta x. Here Wx is the normal mode. In this equation, Wx is the normal mode. Now I differentiate W with respect to x. This becomes minus C1 sine, I'll write the beta in front of it. C1 beta sine beta x plus C2 beta cos beta x plus C3 beta sine hyperbolic beta x plus C4 beta cos hyperbolic beta x. Now I differentiate this equation once again with respect to x. So this becomes minus C1 beta square cos beta x plus minus C2 beta square sin beta x plus C3 beta square cos hyperbolic beta x plus C4 beta square sin hyperbolic beta x. Now again I differentiate this equation. So this becomes C1 beta to the power cube beta cube sin beta x minus C2 beta cube cos beta x plus C3 beta cube sin hyperbolic beta x plus C4 beta cube cos hyperbolic beta x. Now I can use this condition I can use this condition to find my constant. Now I substitute 0 in the equation. So if I substitute 0 here, I get minus C1 plus C3 equals 0. This implies that C1 equals C3. I can use another condition, that is EI at 0 equals minus of K1 W at 0. So this becomes beta cube, I am taking common, EI and beta cube I am taking common. So this becomes minus of C2 plus C4 equals, so minus K1 I am taking on the left side, so that will become plus K1 So in the equation for W I am putting 0. Therefore only C1 and C3 is there when I substitute 0. So K1 into C1 plus C3 equals 0. So let this be the first equation. Now I'll rearrange this in terms of C2, C3 and C4. Now I know that C3 is C equals to C1. I'll put it here. First I'll rearrange this equation. Plus K1 C1 plus K1 C3 equals to 0. Now we know that C1 equals C3, so we can write this as EI beta cube C2 plus EI beta cube C4 equals 2K1 C3. So this can be written like this: C2 minus EI beta cube plus C3 2k1 plus c4 ei beta cube equals 0. Now this becomes my equation number 2. Now again I'll use another condition at end L. So what does this equation look like? C1 I'll replace C1 as C3. So EI therefore the equation looks like this. C2 minus sine of beta L plus, I'm combining the terms of C3 and C1 since C1 and C3 are equal. So C3 equals C3 into cos of hyperbolic beta L minus the coefficient of C1, which is cos beta L, plus C4 sine hyperbolic beta L. This is equals to 0. Now this is the third equation. Now again I can use another condition. K2 into W at end L. Now first I will write the expression for this once again and then I'll substitute. So this expression becomes C1 beta square cos of beta L minus C2 beta square sine of beta L plus C3 beta this is for the second derivative. I'll substitute the terms for third derivative, which is C1 beta cube sine beta L minus C2 beta cube cos beta L plus C3 beta cube sin hyperbolic beta L plus C4 beta cube cos hyperbolic beta L. Now the terms for W in terms of L is C1 cos beta L plus C2 sin of beta L plus C3 cos hyperbolic beta L plus C4 sin hyperbolic plus C4 sin hyperbolic beta L. Now I'll substitute this in the above equation. EI into C1 beta cube sin beta L minus C2 beta cube cos beta L plus C3 beta cube sin hyperbolic beta L plus C4 beta cube cos hyperbolic beta L equals K2 into, I will write the expression for omega at L, W at L, not omega. So WL is C1 cos beta L plus C2 sin beta L plus C3 cos hyperbolic beta L plus C4 sin hyperbolic beta L. Now I'll rearrange the terms. EI, and in place of C1 I will put C3 since I know C1 equals to C3. So in place of C1 I'll put C3. So E1 beta cube sin beta L C3 EI beta cube cos beta L C2. C3 I'll keep as it is plus EI beta cube sin hyperbolic beta L into C3 plus EI beta cube cos hyperbolic beta L, that is C4. Now I'll take the K terms on the K2 terms on the left hand side and again I'll replace C1 with C3. Therefore this will become C3 into minus with a minus K2 cos beta L minus K2 minus K2 sine beta L, that multiplied with C2. C3 I'll keep as it is, C3 K2 cos hyperbolic beta L minus of C4 K2 sine hyperbolic beta L. Therefore, I'll group the terms together. C2 will become minus EI beta cube cos beta L minus K2 sin beta L. Now for C3 terms, I can write this as EI beta cube sine hyperbolic beta L plus EI beta cube sine beta L minus of K2 cos beta L K2 cos beta L minus K2 cos hyperbolic of beta L. This is for C3, and now finally I will write the terms for C4 plus C4 is EI beta cube cos hyperbolic L minus K2 sine K2 sine hyperbolic L. Now we need to set the determinant of this coefficient C2, C3 and C4 to 0, which will give the frequency equation for the system. Now I write the terms accordingly. So this is equals to 0. Now I'll write the coefficients. C2 is, the coefficient for C2 is from the first equation from the second equation, the coefficient of C2 is minus, as you can see, minus of beta cube. Coefficient for C3 is 2k1 and coefficient of C4 is ei beta cube. So I'll write the coefficient for the second equation, minus ei beta cube 2k1 into and ei beta cube. From the third equation, what can I write for C2? The coefficient is minus sine beta L. The coefficient for C3 is cos hyperbolic beta L minus cos beta L. And for C4 it is sine hyperbolic beta L. So I'll write it for equation number 3 now. This was minus sine beta L. It is cos hyperbolic beta L minus cos of beta L. And for C4 it is sine hyperbolic beta L. Now for the fourth equation. So this was the fourth equation. From the fourth equation, I can write the coefficient of C2 as minus of ei beta cube cos beta L minus k2 sine beta L. For C3 it is ei beta cube sine beta L So for the coefficient of C3, I can write this as ei beta cube sine beta L plus sine hyperbolic beta L minus of k2 cos beta L plus cos hyperbolic beta L. and for C4 it is EI beta cube cos hyperbolic beta L minus K2 sin hyperbolic beta L. So this is the determinant, which has to be equals to 0. So this has to be equals to 0. So I can write this as setting the determinants setting the determinant determinant of the coefficients of C2, C3 and C4 to 0, we get the frequency equation. So finally, if I solve this determinant, I will get the frequency equation for this system. Now moving on to the next question. A uniform fixed beam of length 2L is simply supported at the middle point. Derive the frequency equation for the transverse vibration of the beam. Now in this question, we are given a fixed beam of length 2L, which is simply supported at the middle point. So this is the figure. It is simply supported at the midpoint. So this distance is L, and this distance is also L. So here we will set up two coordinate system. Like this is from this end it is x1, from this end it is x2. Now we can write in terms of coordinate x1 first, and the function w is called the normal mode here. So I'll first write the normal mode here, w1 in terms of x1. C1 cos beta x1 plus C2 sin beta x1 plus C3 cos hyperbolic beta x1 plus C4 sin hyperbolic beta x1. Now I'll differentiate this w with respect to x1, w1 with respect to x1. It becomes minus c1 beta sin beta x1 plus c2 cos beta x1 plus c3 here there is a beta, c2 beta cos beta x1 plus c3 beta sin hyperbolic beta x1 plus c4 beta cos hyperbolic beta x1. Now w1 at x1 equals 0, if I substitute, I will get this as C2 plus C1 plus C3 equals 0. This implies that C1 equals to minus of C3. Again, if I put the derivative of w1 with respect to x1 0, we get this as C2 plus C4 equals 0. So these are the two conditions which I get from here. Now what I do, I write this entire equation of w in terms of C3 and C4. Since we know that C1 equals minus C3 and C2 is minus C4. I'll just substitute C3 in place of C1 and C4 in place of C2. Minus C3 in place of C1 and minus C4 in place of C2. So I can write W1 x1 equals C3 cos hyperbolic beta x1 minus cos beta x1. Similarly, with the terms of C4, I can write this as sin hyperbolic beta x1 minus sin beta x1. Now at the point L, W is 0. W1 is 0. So what can I write from here? C3 cos hyperbolic L minus cos beta L plus C4 sin hyperbolic beta L minus sin beta L equals 0. So I will write C3 in terms of C4 now. This can be written as sin beta L minus sin hyperbolic beta L divided by cos beta L minus cos hyperbolic beta L. Now I write the entire expression of W1 in terms of x1, W1 in terms of C4 only. So Wx1 in terms of C4, we can write this as sin hyperbolic beta x1 minus sin beta x1 in place of C3. I'll substitute this expression which I got, sin beta L minus sin hyperbolic beta L divided by cos beta L minus cos hyperbolic beta L. This entire thing multiplied by cos hyperbolic beta x1 minus cos beta x1. So cos hyperbolic beta x1 minus cos beta x1. Let this be the first equation. Now I'll write W2 as a function of x2. x2 is in this direction, as can be seen from the figure. So I'll write W2 as function of x2. W2 is equals to C1 prime cos beta x2 plus C2 prime sin beta x2 plus C3 prime cos hyperbolic beta x2 plus C4 prime sin hyperbolic beta x2. Now I differentiate W2 with respect to x2. This becomes minus C1 dash beta sin beta x2 plus C2 dash beta cos beta x2 plus C3 dash C3 prime beta sin hyperbolic beta x2 plus sin cos hyperbolic beta x2. Now W2 at x to 0 equals to 0. So from this I get C1 prime equals C1 prime plus C3 prime equals 0. This implies that C1 prime equals to minus C3 prime. Again, I put 0 in for x2 for the derivative of W2 with respect to x2. So what I get is C2 plus C4 equals 0. So C2 prime, these are primed, C2 prime equals minus C4 prime. This is another condition which we get. Now for W2 at x2 equals L, it is 0. Now I'll put L in place of x2. So this will become C1 dash cos beta L plus C2 prime C1 prime cos beta L plus C2 prime sin beta L plus C3 prime cos hyperbolic beta L plus C4 prime sin hyperbolic beta L. Now I'll substitute minus C3 prime in place of C1 prime and minus C4 prime in place of C2 prime. So this is equals to 0. Now I'll put minus C3 prime cos beta L plus in place of plus I'll put minus C4 prime. So sin beta L plus C3 prime cos hyperbolic L plus C4 prime sin hyperbolic L equals 0. So C3 becomes minus cos beta C3 prime plus cos hyperbolic L and for C4 plus C4 prime minus cos hyperbolic L. So this is the expression for C3 prime. Now again I'll do the similar process, like I'll express W2 entirely in terms of C4 prime. So I can write this as sin hyperbolic beta x beta x2 minus sin beta x2 minus sin beta L minus sine hyperbolic beta L divided by cos beta L minus cos hyperbolic beta L into cos hyperbolic beta x2 minus cos beta x2. Now I can use a condition. So I can use this condition now. So this can be written as C4 cos hyperbolic beta L minus cos of beta L minus minus sine beta L minus sine hyperbolic beta L divided by cos beta L minus cos hyperbolic beta L. Now again this becomes sine hyperbolic beta L plus sine beta L. I am taking this on the left side, therefore this becomes C4 prime cos hyperbolic beta L minus cos beta L minus of sin beta L minus sin hyperbolic beta L divided by cos beta L cos hyperbolic beta L into sine hyperbolic beta L minus becomes plus, so plus sine beta L. Now this can be considered as so this is one of the equations. Similarly, we can use another condition. We can use another condition. So we can use this condition. So what can I write for this? C4 sine hyperbolic L plus sine hyperbolic beta L plus sine beta L minus of divided by cos beta L minus cos hyperbolic beta L into cos hyperbolic beta L plus cos beta L plus C4 prime gives sine hyperbolic beta L plus sine beta L minus sine beta L minus sine hyperbolic beta L divided by cos beta L minus cos hyperbolic beta L into plus cos beta L. This is equals to 0. Now, the determinant of the coefficient of this C4 and C4 prime is identically 0. So, we set the coefficients of C4 and C4 prime to 0, which gives my frequency equation as I can write this as the determinant of the coefficients Therefore, what we will get is, if we solve this, we will get cos beta L, cos hyperbolic beta L equals 1, and tan beta L equals tan of hyperbolic beta L. This is the frequency equation. So this gives the frequency equation of the system. So what did we solve today? In the first problem, it is asked to find the first free natural frequency of the transverse vibration of the uniform beam of rectangular cross section area, which is given, and L equals 2 meter, E equals 20.5 into 10 to the power 10 Newton per meter square, and density is given. So we need to find this for 3 cases. First for simply supported beam, second is for when both the ends are built in, and third one is when one end is fixed and another end is free. So we calculated the moment of inertia from the given data. From there we know that we know the equation for omega n, which is beta nl whole square root of ei divided by rho L to the power 4. Now we have we first calculated the terms in square root, which came out to be 110.7814. Now, for simply supported beam, we know that beta nl equals to n pi. So for the first natural frequency, n equals 1, that is b1l equals to pi. Now in place of beta 1l, sorry, it's beta not b. In place of beta 1l, we substitute pi. That gives the first natural frequency. Now for the second natural frequency, it's in place of beta 2l, we substitute 2 pi. So this gives the second natural frequency. Similarly, for the third case, we substitute 3 pi. Now for the fixed beam, we know that beta 1l is 4.730841. From there, we calculate omega 1. Again for beta 2l, we know the value. So we get the second natural frequency, which is coming to be 6832.2023 radians per second. And the third natural frequency, similarly, we are getting as 13,393.8474 radians per second. For the fixed free beam, similarly, beta 1L equals 1.87510. We substitute this and get the first natural frequency. For the second case, we get this to be 2441.011 radians per second. And the third natural frequency comes out to be 6834.9030 radians per second. So this is omega 2. Now for the second problem, we are given a beam which is resting on springs on both ends. The spring can deflect only vertically. So in the second problem, we are given a beam which rests on springs at both ends. The springs can only deflect vertically. And the beam is horizontal in the equilibrium positions. So we write W. Now we differentiate W with respect to X 3 times. And then you use these conditions. From the first condition we get C1 equals C3. From the first condition we get C1 equals C3. From the second condition, which we know, we get this equation in terms of C2, C3 and C4, because we already know that C1 equals C3. So I replace C1 with C3. Now we use another condition to get the third equation. Similarly, we get the fourth equation. Then what we do is write the coefficients of C2, C3, C4 in form of a determinant which should be equals to 0, and that gives me the frequency equation. In the next problem, we are given a fixed beam of length 2L which is supported at the midpoint. Here also we are asked to find the frequency equation for the transverse vibration of this beam. Now here we use two coordinates x1 and x2 as it can be seen from the figure. Now for the first case we assume W1 Then we differentiate W1 with respect to X1, and W1 at X1 equals 0 is 0. So from this condition we get C1 equals to minus of C3. Similarly, the derivative of we set derivative of W1 with respect to X1 to 0 at X1 equals 0, which gives me C2 plus C4 equals 0. Therefore, C2 equals minus C4. Now what I do, I write the equation for W1 in terms of C3 and C4. Since I know C1 and C2 in terms of C3 and C4 respectively, therefore now I use the condition W1 at L equals 0. So by using that condition, I get C3 in terms of C4. Now I write the entire equation of W1 in terms of C4. So this is one equation. Again, what I do, I write for the second coordinate x2. Now W2 in terms of x2. Now I differentiate W2 similarly with respect to x2 and set W2 at x2 equals 0 to 0, which gives me this relation of C1 prime and equals to minus C3 prime. Again, derivative of W2 at x2 with respect to x2 at 0 is also 0. So this gives another condition. Now W2 at L equals 0. So using this condition, I got a relationship between C3 prime and C4 prime. Now I substitute C3 prime with and write everything in terms of C4 prime. Now again I have a condition that derivative of W1 with respect to x1 at x1 equals L equals to minus of derivative of W2 with respect to x2 at x2 equals L. So by rearranging, we get this equation. In terms of C4 and C4 prime. So again I have another condition, that is the double derivative of this equation. Which gives another equation in terms of C4 and C4 prime. Now I can say that the determinant of the coefficients of C4 and C4 primes is identically 0. So finally I get this 2 as my frequency equations. So these are the problems that we solved for this week. We will stop here.